Okay, so in this video, we'll be looking at chapter 18, testing hypotheses. So this is another pretty major concept, just like confidence intervals. Uh, it has a lot of the same underlying principles though, so we are going to look at proportions and means for testing hypotheses. So, first off, we're going to learn the steps of hypothesis testing for proportions. And then we're going to look at writing hypotheses, the logic of hypothesis tests, p values, and alpha levels, and then actually doing a hypothesis test of p. And then we're also going to do this with means. So, all of the same learning goals, but for mu or means as well as p. We're going to do them in the same video. Okay, so just a comparison to what we've been doing in chapter 16 and 17. Confidence intervals are used to estimate a population parameter, and it does that with an interval of plausible values. For a hypothesis tests are used to assess the evidence provided by data about some claim concerning a population. So essentially, some sort of claim will be made, and hypothesis tests allow us to determine whether or not that claim is valid or invalid. So, for a hypothesis test, another name for hypothesis test is a significance test. And essentially, that's because what we're doing with the hypothesis test is determining if data is statistically significant enough for us to reject or fail to reject a claim. So for a hypothesis test, the definition, it's a formal procedure for comparing observed data with a claim whose truth we want to assess. So the claim will be some sort of statement about the population parameter. And we always express the results of a hypothesis test in terms of a probability that measures how well the data and the claim agree. So I know a lot of big ideas here, but we're going to have some claim. The claim will be about some sort of population parameter, be it a proportion or a mean. And then we always talk about the results of the hypothesis test in terms of a probability that basically compares the data that we've collected to the claim that was made. So we're going to look at this by looking at one claim, and this is like a real study that was in the news. So Joy Milne believed that she could detect Parkinson's disease by smell alone after her husband was diagnosed with the disease. So she had smelled this smell on him, and then it turns out he had Parkinson's disease, and she believed that that smell was related to his disease. Well, this could have significant effects. Being able to detect Parkinson's early would be major. And so scientists conducted an experiment to determine if she was telling the truth. And in that experiment, she correctly identified 11 out of 12 patients just by smelling their t shirts. So we're going to end up investigating this claim, but this is what I mean by a claim. You can't just say something's true and accept it as is. You have to investigate it. And so hypothesis testing is going to allow us to investigate whether or not this claim is valid. So we're going to come back to this in a moment, but this is what I mean by a claim. So for hypotheses, there are two different types of hypotheses in hypothesis testing. You have your null hypothesis and your alternative hypothesis. For a null hypothesis, just some symbols here. It's capital H with a lowercase 0, so null hypothesis. If you see that notation, it's only used for null hypothesis. And the null hypothesis is essentially the default belief about a parameter's value. So it's the default belief, and we'll get into that more in a second. But basically, that's the claim. This is the belief that nothing significant is happening. The default belief is that nothing significant is happening. Alternatively, the alternative hypothesis, which is denoted with the capital H lowercase a, or subscript a, is the unproven belief about a parameter's value for which we have to gather evidence. So basically, the claim will be the alternative hypothesis, and this is what you're hoping to gather evidence for. The null hypothesis will be nothing's happening, this claim isn't true. So the null kind of defaults to the claim isn't true, and the alternative is that this is true, and we're trying to gather evidence that shows that supports it. And so just a little bit more about the null hypothesis. It's often called the dull hypothesis because it's the one that assumes that nothing new or interesting is happening. And this is the one that basically, when we're doing our statistics, the way we have to do it, essentially, you start by assuming that the null hypothesis is true. And this is kind of like innocent until proven guilty. You assume that the null hypothesis is true until you have convincing evidence otherwise. So when we're doing hypothesis testing, everything that we do is going to be under the assumption that the null hypothesis is true, but it's all going to be in the name of trying to gather evidence for the alternative hypothesis. And so for the alternative hypothesis, again, this is the one that we're trying to gather evidence for. Sometimes it's called the research hypothesis because it's what the study aims to demonstrate. And this is the one that it's not assumed to be true. You have to collect evidence to support it. And so I mentioned earlier, it kind of connects to innocent until proven guilty. So just an analogy, that analogy expanded a little bit. A person on trial is assumed to be innocent. This is the default/dull belief. This is the null hypothesis until proven guilty through evidence. And so the guilt through evidence, that's the alternative hypothesis. And for this, again, innocent until proven guilty. You assume they're innocent. You have to collect evidence and prove that they're guilty. So the innocence would be the null hypothesis. Guilty would be the alternative hypothesis. And from there, there's two possible outcomes. There's either enough evidence to reject their innocent, so we either reject the null, or there's enough evidence to reject their innocent. So this is where we fail to reject the null. Now, this is going to be important, and I'll say it several times. When you are stating your decision from a hypothesis test, you never accept a hypothesis. You either reject the null or you fail to reject the null. And so that's going to be really particular wording, but that's the accepted statistical way of stating your decisions from a hypothesis test. You either reject the null or you fail to reject the null. And so, and that just comes from, you either have enough evidence to reject the null hypothesis or you don't and you fail to reject the null. We never accept the alternative. We never say like, oh, the alternative is definitively true. The only thing we can say is that the null hypothesis is not. So you either reject the null hypothesis or you fail to reject the null hypothesis. Those are the only two ways to state your decision. Reject the null or fail to reject the null. And again, you can never accept the null. It's already assumed to be true, so the research is never proving it. So make sure that's an important concept. You never accept the null because everything that we do in a hypothesis test already assumes it's true. So the research isn't proving that because you've already assumed it. So this is why you're declared not guilty rather than innocent in court. Your innocent was assumed at the beginning. So you're either guilty or not guilty. They don't say innocent or not innocent. It's guilty or not guilty. So your innocence was assumed at the beginning, so your trial's not proving that. So going back to the Smelling's Parkinson's disease. So remember, Joy Milne thought she could spell Parkinson's because she'd smelled it on her husband. In this case, writing the hypotheses for these, remember the null hypothesis is the default dull belief, what we already kind of assume to be true. And at this point, our assumption is that nobody can smell Parkinson's. So the null hypothesis would be that Joy cannot smell Parkinson's. Whereas the alternative, the thing that we're trying to collect information for, is that she can smell Parkinson's. So, how do we investigate that claim? As far as like a numerical hypothesis, because obviously for us in statistics, these are they're not going to be stated in words very often. So, just to put this numerically, Joy cannot smell Parkinson's versus Joy can smell Parkinson's. The way we're going to attach numbers to this, we're going to look at proportions. Remember, she correctly identified 11 out of 12 shirts. So, we're basing this off of proportions. In this case, P is going to be the true proportion of shirts that Joy can accurately identify. P is going to be the true proportion of shirts that Joy can accurately identify. So, to turn this into a hypothesis, for this one, the null hypothesis is going to be that P simply equals 0.5. And that's because, think about this, for the experiment, the null hypothesis assumes that nothing significant is happening. So for this one, if she truly could not smell it, when she was smelling the t-shirts and identifying them, if there was nothing significant happening, it would just be a 50-50 shot of her getting it right or wrong. Like she was either right or she was either wrong. So if she was just guessing, the expected proportion of correctly identified shirts would just be 0.5. And that's the null. P equals 0.5. You always state the hypotheses using population symbols. Notice this is P, not P hat. And then for the alternative, this is the one where we assume that something significant is happening. So for this one, you still have P and you still have 0.5. The null and alternative hypotheses will mimic each other in that manner. However, for this one, if she is not just guessing, if she is really smelling what's happening, like if she can really smell Parkinson's, then her accuracy rate will be higher than just 50-50. So for the null, it equals 0.5. She's just guessing 50-50. For the alternative, if she really can smell it, it's going to be greater than 0.5. So again, the null is what you assume, like nothing exciting is happening. The alternative, something significant is happening here, and we want to gather evidence for that. Okay, so I mentioned a couple things while showing that example. Let's define that a little more. So in any significance test, the null hypothesis will have the form that the population parameter equals some value. The alternative hypothesis can take on many different forms depending upon what the claim is. So sometimes it might be that the parameter is less than the value in the null. Sometimes it's greater than, like the one that we just looked at. And sometimes we might not know if it's less than or greater than, but we think it's different. And so if we think it's different but we're not sure which direction, you could use a not equal to symbol. So again, the null hypothesis, it's always the parameter equals a number. For the alternative hypothesis, it could be smaller, larger, or simply different, or not equal to. And so to determine the correct form of the alternative hypothesis, that's going to come down to just reading the problem carefully and making sure you understand what the claim is, because the claim will be the alternative hypothesis. The hypothesis should express the hopes or suspicions we have before we see the data. It's cheating to look at the data first and then frame the hypotheses to fit what the data show. Hypotheses always refer to a population, not the sample. Make sure you state the null and the alternative hypothesis in terms of the population parameters. And again, before that reason, it's never correct to write a hypothesis about a sample statistic. So for these, you're never going to use p hat or x bar when you're writing your hypotheses. Always p or mu. Okay, so the logic of hypothesis tests and the way they work is a little tricky. So it's again, one of the main basis is that you always assume that the null hypothesis is true first. Everything you do operates under that assumption. Then what you do from there is you calculate how unlikely your sample data is if the null hypothesis is true. You calculate how unlikely your sample data is if the null hypothesis is true. And if it's unlikely enough, you will reject your null. So basically, what we're going to end up looking at is sampling distributions where the null is assumed to be true. And then we're going to figure out how unlikely the observed data is, or the observed sample data is, to determine whether or not the null, like if we're going to reject the null or fail to reject the null. And again, assume that the null is true in order to eventually show that it's false. So that's weird, but you start out by assuming it's true so that you can then prove that it's actually false. So for this, just going back to our Joy smelling Parkinson's example, the logic that we're going to follow when we do this, we're going to start by assuming that the null is true. Say, okay, I'm going to assume that Joy is just guessing. That's how we're going to start it. Then you have to ask yourself, if the null hypothesis is in fact true, how likely is the data that you've gathered? So basically, if she was really just guessing, how likely is it that she got 11 out of 12 shirts correct? If she's just guessing, how likely is it really that she gets 11 shirts right? And then from there, you draw a conclusion. Under my assumption that Joy is guessing, our observed data is unlikely. So I reject my earlier assumption. I'm now convinced that Joy can smell Parkinson's. And we're going to end up being able to calculate some values to back that up. For now, this is the logic that you're going to have to follow. Assume that the null is true. Consider, okay, I have this observed data. How likely is this to have happened given that the null is true? And then make your conclusion based off of that. And so what it comes down to, though, is what is unlikely? Because that could be different depending on the situation. So, at this point, 11 out of 12 shirts, a matter, versus how likely is it versus unlikely? At this point, it's just a matter of opinion. We have not done any statistics yet. So what I'm going to go into next is, okay, statistically, what do we consider likely versus unlikely? And this is where we're going to use p-values and alpha levels. And so the reasoning of significance test, again, we assume that the null is correct. And so just by chance, a very unlikely outcome occurred. The alternative hypothesis is correct. This means that the sample result is not an unlikely outcome. So those are your two options, basically. The null hypothesis is correct, so your observed data is just a very unlikely outcome that happened. Or the alternative hypothesis is correct, and the sample result is not an unlikely outcome. But again, the whole driving idea is that an outcome that would rarely happen if the null hypothesis were true is good evidence that the null hypothesis is not true. So I'll say that again. An outcome that is unlikely to happen if the null hypothesis was true is good evidence that the null hypothesis is not true. So again, this is where I'm going to talk about p-values and alpha levels, because statistically, what does it mean to be unlikely? We have a lot of different things that happened here. For our real data, p-hat was 11 out of 12, 92%. What if she had only smelled 5 shirts and correctly identified 3? Then p-hat would be 0.6. What if she smelled 1,000 shirts and correctly identified 950? Then p hat would be 0.95. So for this, it kind of comes down to which one is more unlikely than the other. And for this one, remember, when we're trying to determine if something is unlikely to happen, we compare it to the null. So, as far as like case B goes, like say she smelled 5 shirts and only got 3 right. 0.6, that's not that far off from 0.5. So, all things considered, 0.6 is more likely to happen than 0.92 or 0.95. It just is, if the null is true. Whereas if the null is true, but we get a p hat of 0.95 or 0.92, that's a heck of a lot more unlikely to happen. If p hat's really 0.5, like if the null is really true and p is 0.5, then this is not likely to happen and this is not likely to happen, but this kind of is. But again, at this point, I'm just basing that off of opinion. So, how to formalize it and what statistical measure actually solidifies likely versus unlikely to happen? And this is where p values occur or are used. So, p value. The definition, first off, p stands for probability. So, p value is a probability value. Now, for this one, for a p value, the definition, this is the probability of observing your measured statistical value or one that is more extreme if you assume that the null hypothesis is true. Again, this is always under the assumption that the null hypothesis is true. It stands for probability value. And again, what this is going to do is it helps us determine how unlikely the sample data is under the null hypothesis. So, based on what it is and what conclusions you would make, when the p-value is low, what that's saying is that the data you actually observed is unlikely to happen if the null hypothesis is true, and you would reject the null. So again, if you get a p-value, a low p-value, that's a low probability. So that's saying if you have a low probability, this is saying that that's really unlikely to occur if this assumption is true. And if you get a low p-value, you reject the null. If the p-value isn't low, the data that you observed is not that unlikely, and so you cannot reject the null. And so this is where if the p-value is not low enough, you fail to reject the null hypothesis. So now we're going to look at how low is low enough. How low is that low? So this is where we have alpha levels. And so the symbol for alpha is this weird looking A. And this is the symbol for significance level. So essentially the reason why it gets this name is what p-value is statistically significant enough to reject the null. And so you can think about this. This is like the cutoff value for p-values. And so essentially, if something is lower than the p-value, that means that it's so unlikely to happen, we can reject the null. The most commonly used alpha level or significance level is 0.05. And so what that's saying essentially is if the probability, if the p-value, if the probability value is less than 5%, because remember 0.05 as a percentage would be 5%. If the probability value, if the p-value is less than 5%, that means that it is so unlikely to occur under the null hypothesis that the null hypothesis must not be true. That's the basic idea behind a hypothesis test. So the cutoff value that we use most often is 5%. If it's below 5%, it's just so unlikely that it must not be true. So the rules for general alpha, again, the alpha that we typically use is 0.05, but you can see different ones. It just will be stated in the problem. So if your probability value is less than alpha, you're going to reject the null. And this means that you have convincing evidence for the alternative hypothesis. If the p-value is greater than or equal to the null, to the alpha level, you're going to fail to reject the null. You do not have convincing evidence for the alternative hypothesis. So this right here, you're going to need to remember this because it's what we base all of our decisions off of. So if it's less than alpha, reject the null. If it's greater than or equal to alpha, fail to reject the null. So going back to our Parkinson's hypothesis test, is there convincing statistical evidence that Joy can correctly identify shirts that have been worn by Parkinson's patients? So if questions are worded like this is your key phrase that means you should do a hypothesis test. In statistics, for our class, the only way that we can gather convincing statistical evidence is doing a hypothesis test. So if you see a question like that, that's what it's looking for you to do. And just a reminder, it's all based off these two hypotheses. Does P equal 0.5 or is P greater than 0.5? And remember, we're trying to gather evidence for the alternative. So just a reminder, in the initial experiment, Joy correctly identified 11 of the 12 shirts. So her P hat was 0.92. What we're going to look at to gather evidence, remember first, we assume that the null is true. So right now, I'm going to assume that the true value of P is 0.50. And then I'm going to ask myself, okay, if P is really 0.5, how unlikely was it that she got a p-value of 0.92? How unlikely is that if p is really 0.5? And the p-value is going to tell us that. So for this one, and I'll show you how to get a p-value here in a moment, but for this one, if I calculate the p-value, I get 0.0019. And so for this one, we would make the decision if it is true that Joy is guessing, the probability that she would get 92% or more of the shirts correctly identified is only 0.0019. So for this one, and I'm going to show you how to get that p-value. So to get that p-value of 0.0019, again, basically you find the probability of getting 11 out of 12, assuming that the null hypothesis is true. Now, what does that look like to assume that the null hypothesis is true? Well, for us, you don't have to go through all these steps, but one way, calculators, normal. And for the mean, for the center, again, if I assume that the null hypothesis is true, then the mean is going to be 0.5. I assume that that's true. The standard deviation, for the standard deviation, you're going to have to remember the formula from chapter 16. Remember, the standard deviation is the square root of p times 1 minus p over n. In this case, I assume that p is 0.5. So for this, I would have to get my standard deviation, I would have to do 0.5 times 1 minus 0.5. And then for the sample size, she was looking at 12 t-shirts. So n would be 12. And if I calculate this, the decimal that I get, that would be, let's see, 0.5 times 1 minus 0.5, 0.5 times 0.5 is 0.25. And so then 0.25 divided by 12, and then square root that, and I'm just going to type that in there. It's this decimal. So that's my standard deviation. So I'm going to put that in there and then click compute. Oh, before I click compute, I got ahead of myself. For the greater, I'm going to, words. I'm trying to determine the likelihood that she got a p-value of a p-hat of 0.92. So greater than or equal to 0.92, and then click compute. Now, again, this is important though. The mean is the assumed null hypothesis. The standard deviation is what you get when you follow this formula. And then we're trying to figure out how likely was it that the observed data happened. And the observed data was a p-hat of 0.92. So greater than or equal to 0.92. The probability of that is 0.0018 with some decimals. I rounded a little differently when I put the value here, but that's how you get your p-value. You calculate the probability assuming that the null hypothesis is the true distribution. So what does this p-value tell me? Because this p-value is small. 0.0019 is small. So for this one, since the p-value is so low, we have serious doubts about our null hypothesis assumption, and we can then reject the null. So for this one, is there convincing evidence? Well, my p-value is 0.0019. So if I use an alpha level of 0.05, yeah, we have convincing evidence. Because the p-value is less than the alpha value, we reject the null. We do have convincing evidence that Joy can smell Parkinson's disease. So this is how you're going to interpret your p-values. If they're low enough, you reject the null and you have convincing evidence. If they're not low enough, you fail to reject the null and you don't have enough evidence for the alternative. Okay, so let's do one from like start to finish. Again, the null is that it will be equal to a claim. The alternative will be different directions depending on what the claim is. So for this one, just to make sure, in chapter 17, we talked about 3 conditions that have to be met before we can construct a confidence interval. And that's the random sampling, 10%, and large counts. Remember, these same conditions will be verified before carrying out a significance test. So again, random, it has to come from a well-designed experiment. 10% condition, when sampling without replacement, you check that the sample is less than 10% of the population. And then for large counts, remember that you have to have at least 10 successes or at least 10 failures. And at least 10 failures. The exact name of this is the one proportion z-test because we're still using z-scores and looking at proportions. But again, the formula will be the same. The mean will be the assumed p-value, assumed population proportion, excuse me, and then the standard deviation formula will be the same. And okay, so for this, you can sometimes use something called the test statistic. Now, I will say for us, StatCrunch will help us avoid having to use the test statistic, but some problems come right out and ask you for it. So what the test statistic is, it's basically like our z-score, where it takes our data and standardizes it. So remember where z equals the observed minus the mean divided by the standard deviation? This is the same idea. So it's basically like our standardized sample data value. So the test compares a statistic calculated from sample data with the value of the parameter stated by the null. The test statistic basically says how far the sample result is from the null value and in what direction on a standardized scale. So again, it's still a standardized score. And you can use the test statistic to find the p-value if you want. StatCrunch puts it to where you don't have to. So again, like I said, it's similar to a z-score. It shows how many standard deviations a statistic or a sample is above or below the null. So here's the general formula for it. P-hat minus the null p divided by the standard deviation of p hat. That's the formula for it. I am going to show you how to calculate it in StatCrunch. And just remember, the larger the test statistic, the more unusual your measurements are under the null. A reminder, the p-value is the probability of getting your observed statistic, assuming that the null is true. And again, we're going to use StatCrunch. So how to use StatCrunch? It is the same exact step as a confidence interval, but instead of clicking confidence interval, you click hypothesis test. But it's still proportion stats, one sample with summary. Same exact steps. And then with chapter 16 and 17, you were picking confidence interval. Now you're going to be doing hypothesis test. And you're just going to put in your value for your null and then select the direction of your alternative. And again, making a decision, it depends on your p-value. If it's less than alpha, you reject the null. If it's greater than, you fail to reject. So for this one, just looking at an example, I'm sure everyone's aware of the Flint water crisis. In 2014, the city officials switched the water source from Detroit to the local Flint River. And then in 2015, residents said that the water is unsafe. The mayor of Flint drank the tap water on TV and insisted that it was safe. But again, the residents were saying that it was unsafe. So we're going to look at, was there convincing evidence that the water was unsafe? Again, for the researchers' claim, it's that the new water from the Flint River corrodes the pipes, so that lead gets into the water. Among many other side effects, ingesting lead can hurt children's brain development. And so to determine if it is unsafe, according to EPA regulations, if more than 10% of homes in a city have high lead content in their water, then the city's water supply is unsafe. So again, we're going to do a hypothesis test. Remember the logic here. Start by assuming that the null is true. So we're going to start by saying, okay, the water is safe. But then we're going to ask ourselves, okay, if it's in fact true, how likely is the data that I've gathered? A lot of homes are getting nasty water, which seems unlikely if the city's water system is safe. And then we're going to draw a conclusion. Under my assumption that the water system is safe, the observed data is unlikely, so I will reject my earlier assumption. So that's the process that we're hoping to go through, but I need to calculate some values first. So for this, according to the EPA, no more than 10% of homes in a water system should have high lead levels. A Virginia Tech study randomly sampled water from 252 homes in Flint. Of those, 42 had high lead content with a p-hat of 0.167. So based off of this, is there convincing statistical evidence that the Flint water system is unsafe? Okay, for starting these, you have to write your null and your alternative. Remember, the null is that it's safe to drink. The alternative is that it's not safe. What this is going to look like for us with numbers, the EPA says that it has to be more than 10% of homes in a city. So the null is going to be that the proportion is 0.1. The alternative is that it's greater than that. And again, P is the true proportion of all Flint homes with high lead levels. And for this, we're going to use a significance level of 0.05. Okay, you have to make sure that your conditions are met. For this, I don't want to spend too much time on this because I don't think that this is the difficult part of this lesson, but the conditions are met here. It's random, the sample size is less than 10% of the population, and we have 10 successes and 10 failures. So we're good. I'm going to show, this slide shows the steps. I'm going to show you this in StatCrunch. So in StatCrunch, let me just get rid of my work from earlier. What you're going to do is, remember, it's the same steps as a confidence interval. I'm going to go to stat. I'm going to go to proportion stats, one sample with summary. and it was 42 homes out of 252. My hypothesis test, you only have to put in two things: the value for the null and the direction of the alternative. And remember, for this, we think it's unsafe, and if it's unsafe, more than 10% have high lead content. If I click compute, this box gives everything you need. This is the test statistic. This is the test statistic, and this is my p-value, 0.0002. And so based off of that, we're going to do our decision. So for this, because our p-value is 0.0002 is less than the alpha value of 0.05, we reject the null. Remember, if it's small enough, you reject. We do have convincing evidence that more than 10% of homes in Flint have high lead concentration in their water supply. For this one, if we're going to look at a one-sided example, remember for this, the reason why it's greater than was that unsafe meant that it was more than 10%. Less than would have been if the claim was like, if you're looking to investigate if something is smaller. And I know we didn't look at one of those, but just you're going to have to read carefully for these. So a one-sided test is when you're testing an alternative in one direction, where the alternative uses a less than or a greater than. I want to look at a two-sided example. So for this one, this would have been, suppose that the claim was just that the high lead content is different from the official. So a city official claims that 10% of homes in Flint have a high lead content. What if the claim had just been that it's different? So that does not specify a direction. There's nothing in the wording that says it's smaller. There's nothing in the wording that says it has to be larger, just different. So if it's just different, this means that it could be higher or lower. And in that case, this is when you would use the not equal to. So if it's two-sided and it's not specifically smaller or specifically larger, that's when you're going to use the not equal to. And again, the specific name of that is a two-sided test. And so again, this is where you want stuff on the low end and the high end. I don't want to spend too much time on that. So for this, just to connect it to confidence intervals, if we did a confidence interval, and I didn't actually take the time to show the steps, but based on the sample data we got, the confidence interval would be 0.12 to 0.213. Is the confidence interval consistent with the result of the hypothesis test? Okay, think about this. Look at the confidence interval. Remember, this is an interval of plausible values. Notice that 0.10 isn't in it. So, is this consistent? Yes, the hypothesis test, we got evidence that we should reject the null. This backs that up. The null is that p was 0.1. 0.1 isn't even a plausible value based on this confidence interval. So you can also back up significance testing with a confidence interval. Again, it's consistent because the plausible values doesn't even contain the null value. Just to connect it to confidence interval, a 90% interval corresponds to a two-sided test with an alpha level of 0.1. Because think about that, 90%, that's capturing everything between two numbers. So if it's a 90% interval, the information at the tails is 10%, whereas a 95% would be a two-sided test with an alpha level of 0.05, and then 99% corresponds to a two-sided test with an alpha level of 0.01. So in general, your confidence level is going to be equal to 1 minus alpha. And just a note, the connection isn't perfect for a population proportion because intervals and tests use slightly different sampling distributions, but it's close. So I want to look at one more example. A 2011 report from the U.S. Consumer Product Safety Commission claimed that 96% of all American homes have at least one smoke detector. Building inspectors visit 400 randomly selected homes and find that 376 have smoke detectors. Is there evidence that the local rate is less than the national rate? Okay, for this one, like for the work, I'm going to just go to StatCrunch real quick and let me show this. So for this example, I'm going to go to proportion stats, one sample with summary. 376 had smoke detectors. So 376 out of 400. And for your hypotheses, for this one, they claimed that 96% of homes have at least one smoke detector. But we want to know if there's evidence that the rate is less than the national rate. So the null here, we assume that the base claim is right. But then the alternative, remember, the alternative is what you're trying to gather evidence for. And we're saying, is there evidence that the local rate is less than the national rate? So I'm going to change this to less than. And if I click compute, this gives me my test statistic and my p-value. Remember, decisions are based off the p-value. So for this, I wrote out the answer here. We have, since the p-value is 0.0207, and that's less than 0.05, we reject the null. There is convincing evidence that the local rate is less than the national average. So for this one, since it's small enough, we reject the null. Okay, so that part of the presentation took a while. I want to show an example of means, but what I'm going to say is not very different from proportions. If you're dealing with means, make sure your null uses mu instead of p. The assumptions and conditions are the same. The only difference is for large counts or normality. Remember that the population distribution can be normal to start with, or your sample size can be larger than 30, or your graph of data from their sample has no strong skew or outliers. So remember, for means, there's a couple more conditions that could be met to satisfy being able to construct a confidence interval or do a hypothesis test. So for this, remember, the mean will still be x bar, but the standard deviation formula is slightly different. And instead of using z-scores, remember, if you're dealing with means, instead of using the normal distribution, we're going to use the t-distribution. That has not changed. So instead of using z-scores, we're going to use t-scores. So we're going to be looking at t-test statistics and one sample t-tests. But same as before, the larger the test statistic, the more unusual the measurements are under the null hypothesis. So again, the same basic ideas are going to apply. It's just going to be slightly different calculations. So the p-value is still the probability of getting the observed statistic, assuming that the null is true, but we're going to use the t calculator. So as far as the steps go, instead of going to proportion stats, if it's a problem dealing with means, you'll go to t-stats. But other than that, the steps are the exact same. So just one last example to close this out. A coffee machine dispenses coffee into paper cups. You might remember this one from chapter 17 video. The machine says it dispenses 10 ounces, but the actual amount varies from cup to cup. And here are the actual amounts. Is there evidence the machine is short-changing customers at a 0.05 significance level? Okay, so for this, I'm gonna look at StatCrunch. Now for this one, remember, you choose with summary if you have summary data. For this one, I have the raw data. I have my list of numbers. So I would type those in. I pre-typed these, but I would type them in. And because I'm looking at averages here, like average cup size, I'm going to go to stat, t-stats, one sample with data because I have my data. Then I'm going to do a hypothesis test. And for my hypotheses, the machine says it gives 10 ounces. So the base claim, the Dole claim, is that it has 10 ounces. We want to know, is there evidence that they're short-changing customers? Short-changing. You have to think about, is that less than or greater than? If it's short-changing, it's less than. So we're going to do less than, compute, and my p-value is 0.012. 0.012. So real quick, I don't have this answer typed in here, but I'll go ahead and add it in just so that you can see me write one out, and it'll be the last thing. For this one, is there evidence that they're shortchanging? The p-value is 0.0012. And since this is less than the alpha level of 0.05, we reject the null hypothesis. There is convincing evidence that they are short-changing customers. So since it's small enough, we reject the null. That's the hypothesis test, start to finish. Let me know if you have any questions after watching.